All right, let's quickly jump into what today's webinar will be about. My name is Lobel and I'm in Digital Rock Physics team at Math to Market. We'll focus in this session on workflows and different approaches, considerations to address uncertainties and results for core analysis, digital rock analysis, rock imaging, and simulations. As such, in these webinars, some of the highlights will be tackling the sandstone digital rock model quality control. Then we'll move into a more advanced porosity analysis, and then turn to wettability effects on multi-phase capillary pressure curves and relative permeability hysteresis. And finally, then we'll conclude with the prediction of mercury intrusion capillary pressure curves at different scales of rock images. Let's start with a little bit intriguing sentence here, that we've been measuring core samples, rocks, for decades, and now the question still remains, are we extracting all the information during the core analysis process, or there is still some information and insights left within the rock sample? So perhaps we need to dig deeper and see another dimension, quite literally, of pore space and understand dynamic flow properties in rock samples. So this is, I would say, the main motivation behind why oil and gas and energy industry is moving from conventional laboratory core analysis towards more scalable core analysis, which includes digital and hybrid workflows. Let's just quickly go through some of the challenges that usually affect special core analysis in labs. And perhaps one of the most important ones is that the results take quite lots of effort. They require expertise, and this all costs money. And even more important, it costs time, as stabilization, for example, of capillary pressure curves takes weeks or even months. And those two concerns, in the end, limits you to how many samples you can analyze. This also related with the fact that different special condition experiments like high pressure, high temperature flooding, or other triaxial mechanics or other types of experiments, they in the end relate to the fact that the results you get, you can't fully be sure of in terms of interpretation. And still, even if all the parameters during the experimental workflows are completely assured, there's still some uncertainty how the flow at plug scale will relate in the end with reservoir performance. And as I assume that most of you in the audience today are familiar with, just look at this image of some quite heterogeneous carbonate samples where you can see different streaks of ultra low permeability formations. And yeah, imagine trying to take out the plugs for analysis from such a core. This all leads basically to the novelty of digital and hybrid workflows, where different types of rock imaging, starting from CD or micro CD or FIB-SEM and other techniques, is used. So these images build into a digital rock model where you can then conduct the virtual experiment and simulations. To this process of imaging, I'll get in more information in next slide. And for now, let me quickly say that the main premise is that the results you get from numerical predictions take much less time, for example, hours or days, in comparison to weeks or even more months in the special core analysis in lab. Furthermore, the multiscale imaging of rock samples also enables multiscale property prediction, which fits more well in overall upscaling towards reservoir scale. And due to the fact that results you get are taking much less time, you can have a much larger throughput or number of samples you will analyze, which in the end builds quite well into different machine learning or AI interpretation and regression models. Here, I would also mention that nowadays there's a big hype behind agentic AI workflows. But nonetheless, such intelligent automation workflows, as I like to call them, they fit quite nicely with this type of digital or hybrid workflows for much quicker automation in comparison to traditional techniques. So I'll conclude this slide by saying that industry is moving from physical-only characterization towards more hybrid and digital workflows. And this transition has started a few decades ago. Now it's getting more and more advanced. So getting to the first part of the whole digital rock physics or core analysis workflow is getting the rock image. So this process starts by taking your core plug or even taking out smaller mini plugs out of it, which are then analyzed scanned in the micro CD device, where the X-ray source is basically shooting X-rays through the sample. Sample is at the same time being rotated, so you get a whole stack of 2D projections of your rock sample. And then the reconstruction software is used to actually generate a 3D model of a grayscale or raw image. And then once you completed this step, next step starts, which is basically going from the raw or grayscale image towards the segmented digital rock model. Here I'll refer you to our previous webinar done by Jonas and Anton, where they go into more details on most important aspects of the image processing and segmentation and which steps are needed for successful workflows at that stage. Feel free to scan the QR code and also visit our YouTube page to find this webinar. Now, I'm going to focus more on what comes next, and this is the simulations, which in the end are most important part of digital rock analysis, where first we need to raise a few considerations. I'll start by getting to this phrase that a realistic-looking digital rock model is not necessarily a reliable simulation model. So what I mean by this is that the digital rock imaging and then also simulations require systematic validation, first of all, of imaging properties like the resolution, sample size, and then also the more detail or consideration of physics behind the numerical solvers. And here, first step, and probably one of the most important ones, is the consideration of image resolution. So here we have to ask ourselves, are critical pore features like pore throats that are important for fluid flow, are they fully resolved or in enough detail? This question has been raised by different authors, different research groups in this area, and I can refer you also later to some of the very important papers in that domain. The second question is the representative volume, which is basically in a trade-off between the image resolution and volume, where we have to ask ourselves whether the rock's volume that was scanned is sufficient for representing the with high conviction properties at that scale of rock properties. For example, porosity, absolute permeability, capillary pressure curves, and other properties. Next question, which is very important for analyzing rocks such as carbonates, is the question of sub-resolution porosity. For example, whether the image resolution that was used is sufficient to capture the multimodal pore sizes, and whether the multiscale rock imaging and upscaling for simulations is needed. And finally, the large and huge question of rock's wettability, which affects not just the digital rock analysis, rather also conventional core analysis. So basically, assumption of single wettability for a rock plug may be fine, but may not be sufficient for capturing quite complex rock fluid interactions, which can be quite diverse across many different facies present in the reservoir rock. And for such, where the petrophysicists need to consider a range instead of single values of wettability that is investigated. All right, so now that I raised a few questions, we'll get to some answers for them and ways to tackle them. First, we'll start by demonstrating a sandstone digital rock model quality control workflow, where we'll use the Berea sandstone sample, which comes from this quite well-known digital rock physics benchmark paper from 2013. Good. Now let me quickly jump to GeoDict, where I'm going to load the Berea rock model. Please note that this rock model was previously segmented. So as I mentioned earlier, this part of workflow you can refer to our previous webinar on image analysis and segmentation. This Berea model has different identified mineral phases, and the largest phase is quartz. Now let me quickly show you how to start the sandstone quality control workflow. This workflow can be found under the GeoApp menu, where we go to digital rock physics and then geometric properties. And here we have the sandstone quality control. Now by clicking on edit, we can see different features that will be considered to check whether the image quality and the digital rock model are good enough for successful predictions of different rock properties. I'll get to more details on those features in a second, where we look at the results from this workflow. So now I would click run. This workflow takes around 10 minutes. So for time's sake, I'm just going to skip to the results from this simulation. So I'm going to quickly drag and drop the results, and let's see what the result file says. So basically, in the top part, we have a summary table, which principally works on the traffic light system. So if any of the two properties that are considered are above recommended values, you're going to land at green. If one of them is between minimum and recommended, then it's going to be in yellow. And finally, if any of the properties is below minimum recommended values, then it's going to be in red. So now about the properties themselves. Without getting into the description, which is here stated, let me quickly explain it on the results of the workflow. So NREV is basically saying how large our domain size is, and is it sufficient enough to capture the microscale heterogeneities. And it basically relates the a number of voxels to the average grain diameter. Why average grain diameter, you may ask yourselves. So the results come from the empirical findings from the reference papers, where the average grain diameters for classic rocks have been shown that if they are higher than 5 and even better higher than 10, the REV for different properties was reached. So this is where the property and also the recommended values come from. Because of this, it's about the grain diameter, this workflow is more suitable for clastic rocks such as sandstones instead of carbonates. But anyway, the second property, to which I'll get in a moment, is also relevant for carbonate rocks. So the second property is the number of voxels that resolve the dominant flow path or percolation path in the structure, which is quite important for precise absolute permeability prediction. In these studies, again, the recommended value was quite similar. It was around 10 to 11 voxels. And as we can see in this case, this scan is quite well resolved with more than 15 voxels in the dominant percolation path. What would be a kind of a recommendation out of this result is to have, if possible, larger domain volume scanned, and you could even have a slightly lower resolution if no other setup of micro CD is possible. Now, coming back to the question of the voxel resolution at pore throats, this is a quite relevant topic, which also relates to how well the numerical solvers can predict the absolute permeability. And for that, I'm just going to quickly jump back to our presentation, where I should mention that if we take a look at this illustration of pore and pore throats, we can already see that at some tighter pores, like this one here, one resolution that you have of your micro CT scan may not be enough to capture in enough detail this pore throat. And this is where we built in 2025 the numerical grid refinement, which basically helps to assure higher numerical accuracy for absolute permeability predictions. We also did a case study analyzing a few different rock samples that are publicly available and where also experimental values have been provided. In this case, we saw a quite nice drop in the absolute permeability towards the experimental values for most of the rock samples. But for example, in this Grossman carbonate, we still saw quite some discrepancy between the corrected absolute permeability prediction and the experimental values. So here the conclusion was that the discrepancy is probably not only from the resolution, but also larger scale heterogeneities of carbonate sample, and also, for example, the representative elementary volume that was scanned in this case. Okay, with that said, we can now move to more advanced porosity analysis, where I'm gonna introduce the Minkowski parameters. I assume also that most of you have heard or even used the Minkowski parameters in your porosity analysis. Anyway, I wanted to bring up this topic as we see that they are quite useful in relating the pore space, pore topology, and geometry to different reservoir flow relevant properties like absolute permeabilities or capillary pressure curves. They basically measure pore volume, then the interface and surface area and integral of the total curvature, and finally the Euler characteristic that basically measures the connectedness between different pores. I noticed, and it's also in many different publications in DRP, it has been noted that so the Minkowski parameters are very good predictors of rock type based correlation, for example, between the pore space and pore geometry with, for example, absolute permeability. So in this case, we ran the Minkowski parameter function in GeoDict on different sandstone samples. And just as an example here, we noticed that the correlation between Euler characteristic with absolute permeability was quite highly negatively inverted, even more so than correlation between porosity and absolute permeability. So now I'm just going to quickly show you also how you could run Minkowski parameter analysis in GeoDict. And for that, let's quickly jump back to GeoDict screen. Minkowski parameters you can find under the Analyze and then MatDict module used for material characterization. And here we go to material characterization submodule, and we have Minkowski parameters. Now by clicking on Edit, we can select for which phase it should be computed. And here in this example, our pore space is under the ID 0, which is oftentimes the default value. So we can just go on, click on OK, and then click on Run. This computation is quite quick and, yeah, as seen, can be done in less than seconds. So this is also one of the reasons why it relates quite well to different, for example, regression models and AI approaches. If you need a very quick quantification in a few values of rock properties. Good. With that said, let's now jump to the next topic, which will be the prediction of capillary pressure curves and relative permeability curves as governed by the wettability and wettability effects on those hysteretic curves. So once again, let me quickly move to the next slide. The main premises in that you can predict primary drainage, then spontaneous or forced imbibition, and secondary drainage in GeoDict. And this is done in the way where you, as illustrated here in the this image on the right side, where first the primary drainage is computed and then both spontaneous and sometimes so forced imbibition if the wettability of the rock is mixed wet or moil or wet. Here it's very important to consider different boundary conditions, such as from which side the invading phase intrudes the domain side, and also by considering different boundaries, you can simulate different types of experiments or even reservoir conditions. Now, very big topic of today's demonstration will be what is the effect of mixed or oil-wet properties on the rock mineral surfaces on capillary displacement and relative permeability curves. So, as I mentioned in the introduction, this is a very important aspect as quite often we try to capture wettability as a single property of rock, but those little fascias present in the reservoir rock are so diverse oftentimes and can have quite different capillary behavior from the past, and also amount of oil that intruded such pore systems. So we have to also consider different amounts of changes in wettability. With that said, I want to quickly explain how the wettability process itself works in GeoDict, so that you also get a better understanding of the parameters that I'm going to show in a moment later. Good. So first we simulate primary drainage, which represents also in the geological terms the initial invasion of the oil into the reservoir rock. And here, this process ends when the irreducible brine saturation is reached, depending on the capillary pressures and the saturations, and in the end, pore geometry. Now, different solid materials can be used for the aging process. So, for example, if your rock has many different minerals identified, like in this case, you could age each one of them individually. Based on the parameter that says how many of the largest pores where oil is present will be affected by the oil touching the mineral surfaces, we can basically combine or overlap the oil distribution and those largest pores that have been selected in the aging process to, in the end, create the age model where we see the aged surfaces where this overlap is present. So as I mentioned earlier, this setup involves also setting different contact angles, and if you use the workflow that I'm going to show in a moment, you can consider different contact angles for up to 4 different rock minerals. So with that said, let's jump back to GeoDict. And let me quickly open this workflow for capillary pressure prediction and relative permeability predictions. It can be found under the GeoApp menu here on top, and then digital rock physics and physical properties. And here there is the hysteresis for all water setups as the second option. Now by clicking on edit, we can quickly see how the setup looks like. So first, the fluids are selected for the primary drainage, which by default is oil, and then also for the imbibition, which again by default is brine. Also, secondary drainage can be computed, and then the wettabilities or contact angles for each of the minerals present in the rock can be assigned. Also, the interfacial or surface tension can be assigned as well. Now, we can simulate for different types of wettability following the primary drainage. So by default, you may have the water wet configuration, where after the primary drainage, so once at irreducible brine saturation, there is no consideration of rock aging. And then you can go with the mixed wet or fully oil wet transition during the imbibition process. So if we go for the mixed wet setting, here we can see how, for example, different contact angles can be adjusted. And by default, the values are 40 for all mineral phases before the imbibition and before aging. And then after aging, you can set what those aged surfaces could have the contact angle. And then the quite important parameter is ascertaining what amount of pore space will be aged based on the largest pores where oil is present, as I explained in the slide before. So we could vary this value from, for example, 10, then to 20%, 30%, 40, and so on. Which is what I did in this on this particular rock sample to see what's the effect of wettability on the capillary pressure curves and relative permeability curves. So now by clicking for OK and then run, we would start the whole workflow, which basically automates many different functions and subroutines that you could also set manually in GeoDict, but which would take much more time. The whole workflow, including the primary drainage, spontaneous and forced imbibition, then the secondary drainage, and also prediction of relative permeability curves, took around 6.5 to 7.5 hours for this domain size of 512 cubed. Where some difference comes from the amount of wettability that was applied. Good. Now I'm gonna open the results from this workflow, and just give me a second. I'm just gonna drag and drop the results where I changed different wettability amounts, so how much the pore space was aged. Now all the result files are loaded, and we can now analyze each of the results individually to see both the capillary pressure and relative permeability curves. And we could also combine the results to actually see the difference in different scenarios of wettability. So let's do just that. Let's select a few different result files and then quickly click on combine results. Important to say is that the simulation command has to be same. So you can only combine the result files from same simulation, in this case hysteresis for oil water setups. Let's click on combine, and here we could also set up more appropriate name, which I'm not going to do in a moment. And then we could now check the comparison of different, let me just go into larger screen. Yes, we could now see a comparison of different capillary pressure curves, so both drainage and imbibitions for different amounts of changed wettability. Now we could also zoom in into specific part of the domain, for example, focusing on the residual oil saturations, or for example, checking what was the turning point between spontaneous and forced imbibition. We could also set in more details the parameters of the plots. For example, setting the axis or the font size or the legend location. I did that in the combined file for all the results. So let me quickly open it and bring it up in the screen. So here I already configured all the parameters before to make it more clear the effects that, for example, the amount of pore space considered for wettability has. As we can see, there can be a quite large degree of variation, which on one side depends on the wettability, but on the other side it depends on the actual pore space of your digital rock model. So this is why having analysis of both properties is quite important. We can now also check the specter of relative permeability curves predictions, where we have on the here going from left to right is the oil relative permeabilities, and here are brine relative permeabilities. And if I hope that the plot is large enough, so if we see, we can see that for most aged rock sample, we got the highest water endpoint mobility, which also goes in trends with the experimental observations. So in a sense, is a good proxy for validating the digital rock simulations. With that said, I would also like to show you one more variation or sensitivity analysis that I did, where I changed the contact angles instead of the amount of pore space that was considered for wettability change. So let's go back to the Hysteresis GeoApp setup. Again, clicking on Edit, where we could now set the contact angles both before the aging, so for the primary drainage, and then again for the aged mineral surfaces after the aging process. So for example, we could just select to age quartz phase, so a material ID 1, and change its initial wettability to 10 degrees. And then also we should make a total sum of 180 degrees, so 170, for the oil wet contact angle for the aged quartz mineral surfaces. Good. And here in the case that I'm going to show you, I had the pore volume considered for aging at 60%. So now again, clicking OK and run would give us results. Now let me quickly open the already pre-computed results, where we can see now the first capillary pressure curves, and quickly just explain what each curve is representing. So the solid curve is from the case where quartz and other minerals had 40 degrees contact angle, and after aging 140. And the curves with the dashed line and points, they had the contact angle of 20 degrees before aging, and then after the aging process, they had 160. What we can see is that there is some effect on the irreducible brine saturation of around 1%. And also some behavior of capillary pressure curves changes when imbibition starts. Other than that, there is also some difference around, again, 1.5% on the residual oil saturations. In any case, for just this variation, we don't see a large effect of contact angles on the endpoint saturations of capillary pressure curve. Now also looking into the relative permeability behavior, we can see that the case with the more, so to say, water wet conditions, which is the contact angle 20 and 160 after aging, we have higher oil and lower brine mobility, which again goes quite well in line with experimental observations. All right, with that said, we now move to the final part of the today's webinar, which is going to be the multiscale workflows for complex multimodal pore throat size distribution rock samples. Good. So let me quickly just explain what it is about and set the scene. Here we have one 2D slice from a micro CT scan of Hysteresis carbonate from Tom Baltris and his group, where we see in black the pore space. In dark gray, it's the mineral phase. However, this mineral phase has a considerable amount of unresolved pores. And then in bright gray, we have the solid phase in this example. So let's say that this bimodal pore throat size distribution is what represents this sample. Then if we had the micro CD resolution of 5 microns, we would resolve those pores that are to the right on this curve, so that are larger than 5 microns, where all the pores that are smaller than 5 microns or around that value, we could not see, so to say, in the micro CT scan. And this is why the multiscale rock imaging and also prediction of single and multi-phase properties is quite important. So now coming first to upscaling of absolute permeability for such samples. Let's start with this Hysteresis carbonate, where we did a smaller crop of 500 cubed. The actual resolution here was 3.1 microns. And again, what we see is, so pores are invisible. Then we have the solid phase in light gray, and then the microporous phase in dark gray. And now, if we wanted to predict the absolute permeability of this whole digital rock model, and we would not consider the microporous phase properties, we would get the approximate sample permeability of around 137 millidarcies. And now let's say that we have a subsample taken out of this microporous domain, which, for example, could be imaged with nano CT ultra high resolution imaging. In this case, we artificially generated this subsample taken from the microporous phase. So let's say that we have this image and that the prediction of absolute permeability of this sample is 1.1 millidarcies. Then by using the Stokes-Brinkmann solver, we could basically populate the unresolved microporous phase in the whole sample to predict the absolute permeability for the whole digital rock model. And yeah, now the question is, what's the effect that those microporous subdomains can have on the actual permeability predictions? So let's jump once again to GeoDict, where I'm gonna first load the Hysteresis carbonate. So now we have our Hysteresis carbonate sample loaded. And as mentioned earlier, so pores are invisible, or here we see only the shadows. Then microporous phase is dark gray, and light gray is the solid phase. And now let's open the results from the absolute permeability prediction, also considering the microporous phase. So here we see that the absolute permeability prediction now is 205 millidarcies compared to previously predicted 137. So let me quickly just open those results as well. So 136.7 and here 200 and basically 205 millidarcies. And this effect comes from considering the microporous phase properties, and is good to illustrate how much of effect multiscale workflows have on precise prediction of not just absolute permeability but also of other properties. Yeah, so in that sense, we're also going to now get to prediction of MICP, or mercury intrusion capillary pressure curves, which then also builds nicely into prediction of capillary pressure curves and relative permeability curves. So let me just quickly also go back to slide and yeah, briefly introduce how the upscaling of mercury intrusion capillary pressure results curves goes. Again, the approach is similar in the sense that we populate the microporous phase that is identified in the whole sample, and we populate it by the predictions of MICP curve that was computed on the subdomain. And then our solver, which is based on the capillary pressure equation, so Young-Laplace equation. This solver now has expansion for considering both continuous mercury intrusion in the whole sample, but also controlling at which point does the intrusion of mercury into the subdomain, into this microporous domain occur. And then in the end, we have the whole range of MICP, and what is more important later, also the capillary pressure curves and rel perm curves for other systems as well. Good. Now let me quickly jump back to GeoDict to show how the this prediction of MICP and upscaled MICP works. So if we go and now open the microporous subdomain, let me quickly open it. So while the sample is loading, yeah, let me quickly jump to the setup for the prediction of MICP curves. So in the GeoDict module here found in predict and then SatDict. We go to mercury porosimetry, and by clicking on edit, we can now, let me quickly just load the default settings. So we can here select from which sides the mercury should intrude into the domain. By default, the two sides are selected, but in most of experimental setups, you would expect the mercury intrude from all sides. And we can also select to simulate the Tomir model, which is very important and neat to get the pore shapes based on the MICP curve. Now, by clicking OK and then run, we would predict the MICP curve for this sub-sample of microporous domain. And now let me go back and load the whole Hysteresis carbonate. Yes. So the simulation takes around 10 minutes. So again, for time's sake, I'm just going to show the setup and then results for finalizing the presentation. So we go into SatDict and then two-phase flow GeoApps, and then upscaling mercury injection capillary pressure to do the upscaling of MICP for the whole sample. Now clicking on edit, again we can select from which sites, and then also the important part is the assigning of MICP curve from the subdomain to its respective material ID. So here we should select for material ID 2, which corresponds to the porous or microporous phase. We should go and select the already predicted MICP simulation. And here there is also the consideration of breakthrough model, which basically controls and checks at which point mercury intrudes from the resolved pores into the microporous phase. The Tomir model is quite neat because it has the displacement pressure, which is one of the identified parameters to basically govern this transition and start of intrusion into microporous domain. Okay, now by clicking OK and then run, we would get the results. Now let me quickly load the results. And here they are. So we get a report with both the pressure saturation, so MICP curve, where in blue the resolved pore space of the Hysteresis carbonate was computed. And then in the red is the MICP curve from the upscale or subsample prediction that is now merged or in a sense in a controlled way related directly to this MICP curve extension. Now we can also check the pore throat size distributions, and this part refers to the pore throats of the whole Hysteresis sample, and then this peak to the left refers to the microporous phase pore throat size distribution. So yeah, now we got the upscaled MICP. All right, in the time of today's webinar, I think we are nearing to the end, and as such, let me go back to presentation to conclude the webinar before moving to the Q&A part. So today in the webinar, we tackled the image resolution and representative elementary volume of digital rock models and how they affect in the end, the numerical precision. Then we looked into a bit more advanced quantification of pore space geometry and how it can relate with different reservoir relevant properties. And then again investigating how the wettability can affect the both capillary pressure and relative permeability curves. And finally, we briefly tackled the upscaling of single and multi-phase properties, for example, for complex carbonate rock samples. With that said, I will also invite you to directly check one of the QR codes. For example, if you want to hear in more details on one of the workflows I presented today, or you want to check out GeoDict yourselves, or also if you want to send a small data set that we can then analyze and discuss with you again in more detail. Thank you very much. And with this, I would now like to head to the Q&A part of the webinar. Okay, so there is one question raised. For the multiscale modeling, how is the microscale unresolved for the solid generated if you don't have the permeability? This is a very good question. So in this example that I have shown, what I basically did was trying to generate a tight or more tight subsample, not considering any particular properties. So in general, the most valid approach would be to have the subdomain imaged, for example, with nano-CT or the FIB-SEM imaging at much higher detail, where you can then segment and directly predict the properties on that model. In this case, what could also be used, and this is more relevant for clastic rocks, so the ones that are based on the grains as the building block, so to say. We could also in GeoDict directly generate the digital twin based on the, for example, experimental grain size distribution. So if you have a grain size distribution available, it can be used for generating a digital rock model directly in GeoDict as well. There is another question coming in. So, hi, is there any benchmarking of capillary pressure and relative permeability obtained by digital rock physics to the ones obtained from traditional SCAL, especially the post-wettability process, such as imbibition and secondary drainage? Very good question. Yes, actually, there have been a few benchmarks. Especially first starting back in 2006, I think, the drainage had a number of also experimental validations. And then as the advancements in terms of contact angles that are considered and the rock wettability that was later added to the poromorphology method, as these advancements were integrated into solvers, then also the benchmarks and validations for imbibition and relative permeability curves have been done. Here I can mention one of the benchmarks done together with the Saarland University. I can also later send you the reference, where the experimental microfluidics result was computed, and on the numerical side we simulated the displacement process as well for different contact angles, and this was done at quite good matching. Then probably more relevant, even more, is the reference or validation study done by Pitt Arnold in 2023, where the both experimental and numerical results from the Gildehauser sandstone that was imaged at synchrotron facilities was done, and then checking how wettability affected the both capillary pressure and relative permeability curves. and in the end quantifying the wettability of the Gildehauser sandstone based on the interpretation of digital simulation results. So again, I can also send you later the paper. There seems to be a few other questions. All right. So one question is, how do we take into account the sub-resolution porosity in GeoDict for the absolute permeability calculation? Previously, you have only shown the final result for the absolute permeability, although you have shown the steps for the capillary pressure. Also, from your previous answer, does this mean that we need the sample for the sub-resolution component? Very good question, and I must admit, due to time, I haven't shown the setup for the absolute permeability sub-resolution inclusion. If time allows, I can quickly share the screen once more, and also show how this would be done. Now my screen is shown. Yeah. So if we go to the predict and then the FlowDict module, which is used for the absolute permeability prediction, and now Stokes-Brinkmann. So I need to note that Stokes-Brinkmann solver is used if you have still resolved one of the percolation paths in your structure. If not, then you need to use the Darcy flow solver. But if you have the one of the resolved percolation paths, then you should use Stokes-Brinkmann solver. So here we go into the setup by clicking on the edit button. And here for this porous, microporous phase, we go and we can now select or set the absolute permeability, and as you can see here, we could now change it according to the value that we either predicted on the for example subsampled rock image, or as I did in this demonstration from the generated digital twin model. And here we could now plug in the value that is relevant for this microporous domain. Okay, and again, just click on run. And the second part of the question was, does this mean that we need to sample for the sub-resolution component? On one side, this was also a question previously raised. On one side, and probably to make the most accurate prediction, yes. For example, having, as mentioned, either the nano CT or FIB-SEM image of the microporous phase would make most sense in terms of precision. Then also, if you had some other property that could relate, which for microporous phase, especially in carbonates, like generating digital twin just from grains would not work. I just did it as a test. Don't do it at home. Otherwise, I would recommend having the ultra high resolution image for such a phase. Good. With that said, let's move to the next question. Hi Lobel, thank you for a very nice presentation. Can you please tell us if it's possible to apply confining pressure in single phase and relative permeability experiments as well as capillary pressure ones? Thank you. Yes, it's possible. This would be done, let's call it uncoupled, but still affecting the results. In one of our past webinars, if we can just quickly share the screen. In one of our past webinars, we focused in more detail on our ElastoDict module, which, for example, has this deformations routine. There I applied different amount of micromodel deformation, and then we could take the result from this deformation simulation and again predict its both absolute permeability or capillary pressure or relative permeability curves. Good. I see there are a few more questions. Thanks, Lobel. Since some of the basic measurements like CD, micro-CD, and SEM are done under no confining stress, can we resolve the influence of confining stress changes? I assume that by this, can you resolve the influence of confining stress changes? The same was meant. So basically, if we apply the confinement, how the different properties will change. So yes, again, first we would run the formation simulation, and then we could do before and after, for example, absolute permeability or capillary pressure curve prediction. All right, then another one, another question. Thanks. Can you comment a bit more about uncertainty workflows with relation to DRP compared to classical lab results, where it's more just an experimental range? Yeah, to be honest, I'm not sure what is here meant by the where it's more just an experimental range. But in any case, I reckon it's meant to be how does the digital rock physics, how can it identify the uncertainty ranges, also from the, for example, standard laboratory procedures. So I may give just one example where, for example, in one study, the experiment was using different gases for the steady state fluid flow and displacement. And then at the same time, there was the in situ imaging. And then the prediction or interpretation of usually quite challenging part in the laboratory analysis. So the interpretation of the saturations and the fluid flows at different saturation steps was done with direct simulation in GeoDict. So basically this was one of those what I earlier mentioned, hybrid workflows, where you can also use the in situ imaging to get the image from the experimental setup, and then use digital rock physics for fast and more reliable understanding of and interpretation of the endpoint mobilities. I hope this, in a sense, answers your question, or at least gives one example of how, in addition, DRP could be related to classical lab results and uncertainties that are in SCAL in the lab. Okay, there is a new questions. How reliable is the simulation of the MICP results? Good question. So as I mentioned earlier, the simulation of MICP is one of our first workflows for capillary pressure displacement, where we used the pore morphology method. So starting back in 2006, there was a number of validations and reference papers to see at different, also inclusions of different contact angles and effects that in the end affect how the saturation of mercury is happening in the pore space. So I would say it's quite reliable, but again, depends on the image quality, so resolution, and the domain size. So as any other workflows that we also discussed in this webinar. All right. And I think, yeah, this ends today's webinar. Thank you once more, all of you, for joining us. Thank you, Jonas. Thank you, Stefan. And yeah, we look forward to greeting you on the next opportunity. Yeah, cheers and talk to you. Bye.